All right, good afternoon, everybody. I'm Luca. This is joint work with Igor and Matthias. Igor's also here in the room. And this paper is about expressions in Java. And it's trying to see where they're really essential, prevalent, and perhaps even neglected. Let me start here with a question. Does, by any chance, here somebody speak German in this audience? Nobody? Okay, that's perfectly fine because we're going to learn some German. So Splash is teaching you useful life skills today. And I don't actually myself. And when you don't learn a language, sometimes the way you want to do it is, nowadays there are all these wonderful smartphones apps. You can download them and you can go through a course in German. And let's try to do that in a small setting here together. So the way we're going to do this is I give you a new word in German, and then we translate it together in English. And so we learn a couple of new words here. Usually you would have sentences in the app. Let's just stick to words for today. So here is a new word, Dampf. And this would be steam. Okay, Dampf, steam. Here is another new word, Fahrt. Fahrt is a ride. Here is another new word, Dampfschiff. And this is a steamboat. Dampfschiff, steamboat. And then we have Donau-Dampfschifffahrt. This is also another new word, and this is a Danube steamboat ride. So by your laugh, I think you probably got that this is not really the ideal way we want to learn German. We learned a couple of words, and that's nice. But after a while, after you get through this course for a little bit, you start to see like new word, new word, new word, new word, and that's sometimes fine. We need to learn new words to speak a new language. But after a while, we see that some words, sometimes a new word results from the composition of words we already know. We have the last one, the one where you all laughed at. That is the composition of Donau, Danube, and Dampfschifffahrt. And Dampfschifffahrt is the composition of Dampfschiff and Fahrt, and again, Dampfschiff is the composition of Dampf and Schiff. Now, we already know this. This is really just like arithmetic. We can take two numbers, 41, 11, and then we can combine them together and we get back a new number. And then we can take another new number and then get back another number. And this is exactly the same we did. Of course, that doesn't work for the whole language, but for this subset of the language we looked at, for certain nouns in German and other languages, you can take two nouns like Dampf and Schiff, and you can combine them together and get a new noun. Now, this is even more general in programming languages. Let me show you a possible example. We can take a string like splash, and then we can call, for example, a method on this string, and then we can, have a number, and then we can access a position on this array. We can have the fourth letter on this array. The nice thing here is that we start with an expression, splash, and then we use another expression construct, the method invocation, to combine and get back a new expression. Then we get another expression, this time very easy, atomic, a Boolean, an integer literal, 3. And then we combine this again together to get another expression, the final one. Now, this is good, and it's very powerful. We get all the benefits of composition, but anecdotally, this is not really the way we teach. This is a quote from a paper last year that says that many programming teachers and introductory textbooks do not emphasize expressions and evaluation, except when it comes to arithmetic and logic. And we seek out to see whether this anecdotal evidence has really some substance behind it. Now, this is not just one isolated quote. Here is a paper from more than 10 years ago that that carry out a Delphi process. So this group, this big study among experts to identify what are the important and difficult concepts in introductory computing courses. And this is barely readable, but I'll zoom it for you. The only two occurrences of the word expression in this table is supposed to represent the entirety of what's needed to learn in introductory programming. The only two occurrences are Boolean expressions and expressions for conditionals. And this really can't be the entirety of expressions in any given programming language. Now, let's see what are the expression constructs in Java if they are not just arithmetic and logic. Here's one example. We have an array access that is an expression construct. So here's our notation to describe the structure of such a construct. We have sub-expressions, in this case for the index and for the target of the array access expression, that are denoted with this orangey E. And we have the tokens of the Java language, in this case the square brackets, with the blue color. Here is a more complicated example for method invocation. Now, in its basis form, a method invocation could be just the name of the method represented there with identifier, and then a couple of parentheses that are always needed, and possibly one or more arguments if we want to give them. Now, this is not, of course, the whole structure of the construct. There are several variations. We can have, for example, a method invocation with an explicit target. So we are really passing the reference to the object before the E, and that's, again, an entire sub-expression. And then we might also have like static method invocations. That means that we have a reference type that can be on the left-hand side of the dot. Finally, we might even have more complicated method invocations when we have type parameters, and we can have several type parameters here. So this is the structure of a method invocation expression, and we compile this structure quite carefully for all the expression constructs in Java. You can see this in the paper. We have quite a rich table that goes and does exactly what we have seen together, trying to distill the structure of these constructs for the entirety of the language that is about expressions. Now, if these are the constructs, how are they taught? To do this, it's really hard to assess how things are being taught in general. We have so many courses and so many universities. What we can easily look at is textbooks. We looked at 6 recently updated textbooks for introductory programming that are focusing on teaching Java. And we looked at 2 things. For each expression construct, are there misleading explanations about the constructs and its sub-expressions? And after a construct, usually the textbooks have a section that tries to exemplify it with a bunch of code snippets, and maybe then also some projects. And we also looked at those sections immediately following the introduction of a new construct to see whether there were some code examples showing non-atomic sub-expressions. Because if students get only shown atomic sub-expressions, they might be induced to believe that that's not really a full sub-expression that can be plugged in with an entire other expression. And here is what we found. Here are some examples of what we consider to be misleading explanations. A quote: to call a method, one uses a variable that contains a reference to an object. There's an explanation for the method invocation on an instance. And that's not really true. I mean, we have just seen an example. We're calling the to-car array method on something that is clearly not a variable. That's a string literal. Here's another quote. An index is an integer expression written between square brackets following the name of an array variable. Now, here we have an array access expression, but what's on the left of the square brackets is not really a name. It's an entire expression. It might be a name in simple cases, but that's not showing the full flexibility of the language. To summarize, most constructs are properly described in textbooks, but sub-expressions are much more neglected. For example, the target of the array access expression is described with misleading sentences in 4 books, And the same goes for the target of a method invocation. And these are not too far-fetched constructs. These are kind of some of the most basic constructs in the language. And for examples, for code examples, the target of the array access expression is shown using only atomic examples in all of the books we have surveyed. But okay, we have seen that expressions, there are several expression constructs, but I mean, Java is a language that is so big, maybe there are so many other things in the language, and it's okay not to teach expressions so much. I mean, it's not a functional language, maybe there is so much, so many other things in the language. So here is an algorithm, for example. It's a method that implements a binary search textbook, classic example. So let's say that expressions are not so important. Let's try to get rid of them. Let's see what we end up with. So we have that the right-hand side of all assignments is an expression, and also assignment itself is an expression in Java. And so we get left to the declaration of the mid variable at the very beginning, and then we got rid of the assignments in the middle. Now we still have conditions here for the if, the else if, and the while. There are also expressions, and so let's get rid of those too. Once we get rid of those, we can't really have those constructs because we can't have a while without a condition, and the same goes for the if. And so we will also remove this. What's more, also here we have -1 at the very end, which is an integer literal, and that's also an expression. And so we can't even return this method. Given that Java prescribes the method that has a signature of type int needs to return an integer value, we really cannot have that as well. And so basically, without expressions, we cannot even compile this method. Now, some of you might say, well, this is a kind of an example, but there are so many other examples in the language that I could try and do the same trick you did there that would not show such a small code. And this is what we did in the paper. We started from the entirety of the grammar in Java, and we removed all the grammar productions that are expressions. And we transitively removed the constructs when it's not possible to have the expression anymore. And this is what we end up with. We end up with this snippet of code that is the entirety of Java that one can write without having expressions. And that's really, I mean, there are some important things here. There are class definitions, there are instant interfaces definitions, there are some for loops that don't achieve much, but this is really everything we can do without expressions. And so basically, we see that expressions are really needed to carry out computations. Now, if expressions are so varied, do students use expressions in their own code? We wanted to investigate what happens in a typical Java program written by students. And we look at 3 aspects of this question. The first one, how many expressions are there? How many expressions are in the code that students write? What is the structure of those expressions? And which kinds of expressions do students actually use? To do this, we analyze the black box data set, which is a data set of student code that contains anonymous submissions from codes written within the BlueJ IDE, which is a pedagogical IDE that several universities and high schools adopt. We mined 90,000 repositories with almost 1 million Java source files. And here's the answers. Here are the answers. First question, how many expressions are there? Well, if we look at just the number of tokens, we see that the majority of the tokens in the median projects are dedicated to expressions, 53%. And the median method contains 40 expression constructs. Now, this might say something about the size of methods in general people tend to write. It's also really showing that expressions are everywhere. And note that counting this and reporting this statistic is not entirely trivial. For example, for expression tokens in Java, you have some situations in which the descendants in the abstract syntax tree, the descendants of an expression node might not be expressions themselves. For example, when you have a class instance creation that also defines an anonymous inner class, there you have in the abstract syntax tree some nodes that are descendants of an expression node that are not expressions themselves. And if there are expressions inside those, they are not even the same expression of the outermost one. And for the same reason, it's also particularly tricky to count what is a method, because you might have method definitions, in this case of the anonymous inner class, inside an expression. About the structure of expressions, that there are more than three expression constructs in the average expression. And if we look at the tree of these expressions, these trees have more than two levels in general. Now, what do these numbers mean? Well, when the tree of an expression has more than two levels, that is basically telling us that to understand that piece of code, to understand that expression, students need to understand the recursive nature of expressions, need to understand that you have a parent, there's an expression, you have a child, there's an expression, and that child being an expression can be, again, a parent of another expression, and so on. Final question, which kinds of expressions are used? We have a lot of interesting data there, but I'll spare you the details. You can find them in the paper if you're interested. So here is the takeaway from this paper. We have seen that expressions are essential in Prevalent. Also in languages like Java that are non-predominantly functional. And we have also seen that textbooks, at least partially, neglect expressions. And there is a risk that we might do the same in teaching. Now, how can this paper help? Well, we're offering, with the table I've shown you before, a comprehensive reference that describes the structure of all the expression constructs in Java. And you could also adopt the same process we use to analyze textbooks to check and improve how you're presenting or teaching expressions, to see whether you're really covering all the expression constructs and the subcases using sub-expressions that are not necessarily atomic. And this is it for our paper. I'm happy to take questions.
So we do have time for questions. Please go ahead.
So we have one in the room. Let's see whether we can reach with the microphone so that people online hear it as well.
So, yeah, so this is more perhaps a comment than a question, but I think these expressions. So being a TA in these types of programming courses, I often see that students struggle with if statements, and they will see that in an if statement you should put something equals or is larger than or less than something else. This is what goes into an if statement, and understanding that this is actually a Boolean expression, and all the powerful things you can do from that. So yeah, this was
that's very interesting. So I think that's an instance, the exact case you're reporting, it's an instance of students not really seeing that atomic things are expressions. Like sometimes we say, like, you have already a variable that is of type Boolean, and to check, to use that in a condition for an if statement, they write variable equals true. Exactly. And they don't see that that variable is already in itself an expression. And we actually documented several of those programming misconceptions. This is what we call in earlier work. So we have a website that contains, I think, more than 200 misconceptions for Java, and some of them are exactly describing what you're saying, the fact that they need to compare with a Boolean literal, or that they don't see that atomic elements are expressions. So that's very interesting.
add to that our experience with first year programming in a Java-like language, semicolons after the first if line. So if,
Oh, that's a bad one.
yeah, so they write the top line of the if and they put a semicolon in the rest of their
Uh-huh.
and that's exactly the same misconception, right? It's like I'm treating this thing as if it's by itself.
Yeah, they're not really seeing that the if statement is a compound construct that can have then an entire block. Yeah.
I have a question about the implication about this finding. So, do you think there's any applications of your finding for the program analysis for Java programs? For example, maybe some expressions contain the same sub-expressions and such things can be reused, or maybe such information can be used for the optimization of the Java program.
Mm-hmm. Well, I guess we have several. I mean, in general, there exist quite sophisticated program analysis tools that already look at and treat not only expressions but also the other parts of the language, and to do things like compiler optimizations or this kind of stuff. But an interesting thing is that if somebody, for example, would want to replicate this study for another language or do some kind of program analysis tools, we are releasing the whole infrastructure we use to do the studies, and the statistics is already available as a GitHub project. And so you can also check it out and use it if you see like possible extensions or uses for program analysis that we haven't anticipated.
Hi, just a comment. My name is Agustín Martínez. I'm from Argentina, Universidad de Buenos Aires. I also agree with this idea in teaching that students have problems with Booleans in particular. More problems than with numbers. And the model of numbers, natural numbers, fractional numbers, are very more complex than Booleans. Booleans are very simple.
Mm-hmm.
But in the school, they are not presented as numbers are. So I think there is the origin of the problem. In programming, it's very common to use Boolean. And Booleans and numbers combined. When you compare two numbers, you get a Boolean. So they are related. That's the comment. And also, I will show in my presentation on Friday, I will show a new visual language where children can represent Booleans by themselves. They can build Booleans, and they can build if then else notation with the Booleans they made, all with drawings.
Mm-hmm.
But I invite everyone to see the presentation. And I think the solution to the problem in the educational aspect is let's teach them the Booleans as we teach the numbers. They have to build, operate with them. That's the path.
Yeah. So I think we don't have more questions here in the room. Not for online. I'm not checking the chat.
Well, actually, I do have a question. I've noticed that you focused on expressions in Java, right? And I'm just curious. I mean, are you convinced that Java is a most suitable language, for pedagogical purposes, right? So if we're talking about expressions, do you think it's, in particular, I'm interested, how you feel about Java as the first language, for introducing students to programming altogether, right? And that's basically my question. Okay.
Yeah. So let's say I'll refrain from making comments that will start a war on what is the best language for CS1. But I can. So my point here being, well, there are some expressions, all the functional ones, that for which expressions as definitions are 100% of the language, and so we can build and leverage on all the knowledge you were describing very well in terms of math. We have an understanding from math that we can compose things. We have operators, we have unary operators, we have binary operators, And so there are languages that functional languages that try to make that basically the entirety of the language. And so that could be, in my opinion, a good way to start. But our point here is, even if one decides to start with Java, and there are a million reasons for why one would want to do that, let's not ignore expression. Let's not say, oh, Java is not a functional language, therefore I'm not teaching expressions, because then we see exactly the kinds of misconceptions people in earlier questions were mentioning.
Okay, fair enough. Thank you.